Hello, my name is Wanye, and today I will be presenting our work on the parallelization of Markov chain Monte Carlo methods for community detection. This work was done in collaboration with Vitaliy Gleyzer and Edward Kao of the MIT Lincoln Lab and advised by Dr. Wu Feng. We will start with a general introduction to Markov chain Monte Carlo methods, which are a set of techniques for sampling from unknown distributions, and these techniques are based on Markov chains. The term Monte Carlo refers to the process of taking random samples in order to obtain some sort of numerical result. And the idea is that as you take more samples, the distribution of the samples gets closer and closer to the target distribution. This happens because of the use of a quality function, which is based on some known information about the target distribution and is used to accept and reject samples. The process of taking these samples ends up building the Markov chain by ensuring that a sample taken at any given time step t depends only on the internal state of the sampler at the previous time step. This time-based dependencies within the Markov chain end up creating a chain of dependencies, which forces the execution of Markov chain Monte Carlo methods to be inherently sequential. As such, they are computationally heavy and generally not practical for use on large datasets. However, they have good convergence properties and are therefore really accurate when modeling complex distributions, and as such are one of the main workhorses in modern statistical inference. As such, there is a need to accelerate Markov chain Monte Carlo methods, for example, through parallelization, in order to make them more feasible and practical for modern big data scenarios. In our work, we focus on applying parallel Markov chain Monte Carlo methods to the problem of community detection, which is analogous to graph clustering and can be thought of as the grouping of vertices into strongly connected groups. This is an important problem because it is used across several domains, including security, social media analysis, and bioinformatics. But optimally performing community detection is NP hard, and therefore this can only be done by heuristics and/or optimization techniques, such as Markov chain Monte Carlo techniques. One of the interesting things about community detection is that the statistical dependencies between the vertices in a graph are encoded entirely within the graph structure for community detection. We know that real-world graphs are sparse because they tend to follow the power law degree distribution, and therefore we have this hypothesis that the sparsity in the statistical dependencies and in the graph structure makes parallel Markov chain Monte Carlo suitable for performing accurate community detection. There are two key takeaways that we'll present in our talk today. The first one is that we parallelize Markov chain Monte Carlo methods, which are inherently sequential, and we managed to do this without sacrificing accuracy. In our talk, we'll present empirical results on both synthetic and real-world graphs that show that our parallel method produces significant speedup and maintains the accuracy of sequential Markov chain Monte Carlo for community detection. Additionally, we present a novel metric for measuring the accuracy of community detection in the scenario where there is no ground truth. However, in the real world, this is every scenario because if you have ground truth, you're not going to be running community detection in the first place. Having gone over the introduction, the rest of the talk will follow this agenda. We'll start by providing some background information on how community detection and Markov chain Monte Carlo methods fit together, as well as some of the challenges in parallelizing Markov chain Monte Carlo methods. We will present our hybrid parallel Markov chain Monte Carlo method, as well as the asynchronous Gibbs technique on which it is based on. We'll provide some results on synthetic and real-world graphs, including introducing our novel metric for measuring accuracy in the real-world scenario, and then we'll conclude with a summary of our results. The first bit of background has to deal with stochastic block models. These are essentially matrices that quantify the chance of an edge forming between any two vertices in the graph based on their community membership. The distribution that the Markup chain Monte Carlo method is going to be modeling is the distribution of all the possible block models which can be formed from a given graph. And these block models are formed by changing the community membership of either individual vertices or sets of vertices. The quality of any given block model can be measured using the minimum description length equation, which is shown at the bottom here. For the sake of time, we will not go over the entire equation, but for the purposes of this presentation, you can abstract it to a function that makes use of the size of the graph, the size of the block model, and the connectivity within the graph. To perform community detection, we apply Markup chain Monte Carlo methods in the stochastic block partitioning algorithm, which was developed by Tiago Peixoto. This is an iterative and agglomerative algorithm whose aim is to optimize the minimum description length for a given graph. It starts by assigning each vertex to its own one vertex community, and then entering the set of global iterations. The purpose of the global iterations is to perform a golden ratio search for the optimal number of communities within the graph. And what this means is that when using stochastic block partitioning, you do not need to know or guess the number of communities within the graph a priori. The algorithm will automatically determine that for you. Within each global iteration, the algorithm performs two phases. The first phase is the merge phase, where entire communities are merged together into larger communities based on the change in minimum description length. And the second phase is the Metropolis Hastings phase, where individual vertices get a chance to switch their community memberships, again, based on the change in minimum description length. After some number of global iterations, once the minimum description length has been optimized as far as the algorithm can take it, the output of the algorithm is the community membership for every vertex within the graph. The Metropolis Hastings phase is the only strict Markup chain Monte Carlo portion of the algorithm, and therefore everything that we change, all our implementations only deal with this Metropolis Hastings phase. Everything else, which is outlined in blue here, is going to remain constant for the remainder of this presentation. Here is the runtime breakdown of the stochastic block partitioning algorithm. We can clearly see that the Markup chain Monte Carlo phase takes up anywhere between 80 and 99% of the runtime of stochastic block partitioning, depending on which graph you run stochastic block partitioning on. This is partially because the Markup chain Monte Carlo phase is sequential, and also partially because it is iterative, which means that within each Metropolis Hastings phase, the algorithm makes several passes over every single vertex within the graph before the Markov chain stabilizes. As such, parallelizing the Markov chain Monte Carlo phase is going to lead to the most benefit in terms of speed up for stochastic block partitioning. However, there are some challenges in parallelizing Markov chain Monte Carlo methods, one of which is the number of dependencies. Although we know that the statistical dependencies within the graphs are sparse because of their sparse structure, the dependency chain that ends up forming as a result of the Markov chain ensures that every vertex move depends on all the previous vertex moves within the chain. If you follow this all the way down to the bottom of the chain, that last vertex move is going to depend on every single vertex move that happens before it. Because of this, we end up with a large number of dependencies and traditional parallelization methods where a worker, after performing a vertex move and changing the internal state, has to communicate that state to every other worker that needs this information. Is going to lead to way too much communication happening, and the algorithm will not produce any noticeable speed up. We also have the problem of linear dependencies, which are, again, a product of the Markov chain and the sequential dependencies within it. Breaking these dependencies often leads to poor convergence because we break the assumptions under which Markov chain Monte Carlo methods work. In our approach, we aim to limit the effect of both of these challenges by limiting the amount of communication that we perform, and also by selectively breaking dependencies, such that we only break dependencies which do not have a large effect on the community detection problem. And therefore, those are the dependencies which we can afford to break. Moving into our method, we first provide some background on the important parts of the Metropolis Hastings algorithm, which is what was originally envisioned for the stochastic block partitioning algorithm. This is a well-known traditional sequential Markov chain Monte Carlo method, where all the dependencies within an iteration are being respected. That is to say, whenever a vertex changes its community membership, that change is immediately applied to the block model, and then the next vertex in the processing queue performs its vertex move using this updated block model information. There is an alternative to Metropolis Hastings. This is a parallel MCMC algorithm that exists in the literature and is known as Asynchronous Gibbs. It is also known as the Hog-Wild method. It was also further refined by Turenin et al. In their exact asynchronous Gibbs algorithm, which we then adapt for the community detection problem. The main difference between Metropolis Hastings and this asynchronous Gibbs algorithm is that the asynchronous Gibbs algorithm does not consider any of the dependencies within a given MCMC iteration. What this means is that every vertex is working with a block model that is stale by up to an entire iteration. As such, within this algorithm, a large number of dependencies ends up being broken within every iteration, which leads to unpredictable accuracy results. However, those broken dependencies also allow the algorithm to be embarrassingly parallel, which makes this algorithm very scalable and fast. So comparing these two approaches, one of them is inherently sequential, but has a really high dependable accuracy, whereas the other is embarrassingly parallel, which makes it really fast, but the accuracy is unpredictable and varies from graph to graph. Our contribution is a hybrid method, which takes the best of both worlds. Our method is parallel and is highly accurate, and we will show later on that the accuracy of our hybrid method matches the accuracy of the sequential Metropolis Hastings method. Our hybrid approach is based on a finding by one of our co-authors, Edward Cow, which states that the community information content within any given edge in the graph is proportional to the product of the vertex degrees of the vertices that make up this edge. For example, the central edge in the green graph below contains more community information because the vertices that make up that edge have higher vertex degrees, which is to say they have more neighbors than the vertices that make up the blue, the central edge in the blue graph. In our case, the stochastic block partitioning algorithm is vertex-based and not edge-based. So we approximate this finding by reformatting it as higher degree vertices generally will contribute more towards community information than lower degree vertices. What we know about the vertex distribution in real-world graphs is that the number of high degree vertices is typically low because real-world graphs follow the power law degree distribution. And this allows us to perform, to plan our parallelism based on the graph structure. We can find the higher degree vertices and process them first sequentially using the Metropolis Hastings algorithm, and then take the remaining majority of the vertices which have relatively low vertex degrees and process those in parallel using the asynchronous Gibbs algorithm. By doing this, we end up respecting the few very important dependencies within the graph, and break in only the dependencies which do not have much of an impact on the community structure in the graph. We test our approach using several synthetic and real-world graphs. We use synthetic graphs because this allows us to modify the properties of the graph, which may affect the accuracy of the results. We do so by varying parameters like the degree distribution and the strength of the community structure, among others, in the block models which we use to generate the graphs. We also look at 14 real-world graphs, which span several domains, including social media, co-purchasing networks, and web graphs, but these graphs have no ground truth. For each graph, we run each algorithm, that is to say, stochastic block partitioning using the original Metropolis Hastings algorithm, stochastic block partitioning using the embarrassingly parallel asynchronous Gibbs algorithm, and stochastic block partitioning using our hybrid approach 5 times. This is done because the stochastic block partitioning algorithm is stochastic. That is to say, it produces a different result every time it is being run. And for such algorithms, it is common to run it multiple times on every data set and pick the best result. We do the same thing here by picking the best of 5 runs. That is to say, the run that produces the lowest minimum description length for each graph. And as an additional note, the block merge phase that is being used for all of our runs is parallel. This is not the MCMC phase, so we do not describe or focus on it. And the block merge phase is embarrassingly parallel, so there's really no reason not to do that. In terms of hardware, we run our experiments on the Tinkercliffs cluster at Virginia Tech, where every node has 128 cores and 256 gigabytes of RAM. We start by looking at our MCMC phase speedup results on synthetic graphs. As can be seen here, the green bars representing the asynchronous Gibbs variation of stochastic block partitioning are the highest. So asynchronous Gibbs produces the highest speedups, which is not surprising considering that it is embarrassingly parallel. The hybrid approach is somewhere in the middle, so it still produces speed up compared to the sequential stochastic block partitioning method. It's just not as fast as the synchronous Gibbs. However, where the hybrid stochastic block partitioning method shines is when you look at the accuracy result. You can see that on graphs like S4 and S6, asynchronous Gibbs produces accuracy that matches the sequential stochastic block partitioning method. However, on graphs like S5, asynchronous Gibbs leads to a significant reduction in accuracy. And on the 6 graphs outlined in red here, the asynchronous Gibbs method completely fails to converge. That is to say, every single vertex within the graph ends up lumped into one giant community, which means that the information content within the resulting partition is 0. On the other hand, our hybrid stochastic block partitioning method matches the accuracy of the sequential stochastic block partitioning algorithm across all the synthetic graphs that we tested. Thus, so far, we have shown that we can parallelize the inherently sequential Markup Monte Carlo method using approximate computation via the asynchronous Gibbs algorithm. We showed that using the pure asynchronous Gibbs algorithm leads to the fastest results, which are up to 7.6 times faster than sequential MCMC. But the asynchronous Gibbs algorithm does not always converge. And at least in our case, we were unable to find any measurable graph properties that can predict whether or not asynchronous Gibbs is going to converge. In our paper, we talk about this influence metric, which was previously proposed to do just that, but it is infeasible to compute influence on any large graphs due to its computational complexity. On the other hand, the hybrid approach, which we introduce, although slower than asynchronous Gibbs, still provides speedups up to 2.7x over sequential Markup Monte Carlo, and it is just as accurate as sequential MCMC. Having shown that our method works on synthetic graphs, the next step is obviously to test whether it works in the real-world scenario. However, real-world graphs do not have ground truth labels for their communities. Typically in this scenario, researchers would use the modularity metric as a stand-in for accuracy. However, modularity has some well-known problems, one of which is that modularity has been previously shown to not always correspond to the best community labels for a graph where they are known. This can be seen in the bottom left chart, where if you plot the correlation graph between normalized mutual information, which is a measure of accuracy, and modularity for the synthetic graphs, which we talked about earlier, the R-squared value is 0.59, which means that the only 59% of the variation in accuracy can be explained by the variation in modularity. In order to improve upon that, we introduced this normalized minimum description length method, which is based on the minimum description length equation that we talked about earlier. To calculate the normalized minimum description length, you simply take the minimum description length of the block model produced at the end of community detection and divide that by the minimum description length of a null structureless block model where all the vertices belong to one giant community. We show in the bottom right chart with a correlation plot between normalized MDL and normalized mutual information that the normalized MDL metric has a much higher R-squared value of 0.87 compared to 0.59 for modularity, showing that our metric corresponds much better to known accuracy metrics than modularity. And therefore, we use our normalized minimum description length method to measure accuracy for the remainder of this talk. And here are the results using normalized MDL on the 14 real-world graphs that we selected from different domains. And we can clearly show here that our hybrid approach matches the accuracy of stochastic block partitioning on all the real-world graphs that we looked at. At the same time, our hybrid approach provides significant speedups of up to 5.6x over sequential MCMC. There is a slowdown on only one graph, which is BART5, but this graph is really small and very sparse, and therefore there isn't enough parallelism to draw out of that graph using our method. To conclude, as we mentioned in the introduction, Markov chain Monte Carlo methods are some of the most commonly used methods for statistical inference due to their accuracy and convergence properties. However, they are computationally demanding and inherently sequential, which limits their practical applications to contemporary big data scenarios. In this work, we present the new hybrid Markov chain Monte Carlo methods, which succeeds in parallelizing the inherently sequential MCMC problem, providing up to 5.6x speedup over sequential MCMC on real-world data. When we apply this to the community detection problem, the overall algorithm speedup goes up to 4.2x, showing that our method does not induce significant overhead. And we are able to produce the speedup numbers with little to no accuracy over sequential Markov chain Monte Carlo methods. As such, we believe that our work paves the way for parallelizing Markov chain Monte Carlo methods without losing accuracy for other applications as well, thus making it a more attractive option for contemporary real-world scenarios. Thank you for listening.